Okay, I have come back to ocean intraseasonal variability. I found some good papers that talk about feedbacks from the ocean to MJOs and even hypotheses of ocean waves triggering some MJOs. So we will look at MJO timescale feedbacks from the ocean under ocean ISVs, and then I will show lower frequency feedback between MJOs, the ocean, and back to the MJOs. So these two podcasts I'm going to add based on a few papers. These few papers from Rydbeck et al. Working with Tommy Jensen and Andy Weber. So US and UK teams working on some really nice papers. Somebody's ringing the doorbell. Okay, sorry about that. Yes, this is what happens when you are recording at home. So, Rydbeck et al. And Andy Weber and the team have been producing some ocean interactions with intraseasonal variability. This is the first paper that argued that when you look at sea surface temperatures, we have the conclusion that we have always understood that when there is a convective phase, this is in the Indian Ocean looking at 10 south, 10 north, you can see the Sri Lanka and southern tip of India here, and part of Sumatra and Thailand and so on, East Africa. So when there is a convective phase, there is cooling of sea surface temperatures, cyclonic circulation, or westerlies and easterlies creating entrainment and surface cooling. And in the suppressed phase of the ISO, we get the other way, we get a warmer sea surface temperatures, and we have always argued about how sea surface temperature warming precedes the convective phase and how SSTs get reorganized after a convective phase. So obviously we are looking at OLR as well, so negative OLR corresponds to rainfall, and convective phase positive OLR anomaly at intraseasonal timescale corresponds to suppressed phase of the convection, as you always remember. But if you look at the same thing in terms of ocean heat content, then you see that there are these patterns with negative ocean heat content anomalies here and positive heat content anomalies off the equator here, and that's really interesting. These days listed here in each panel, in these two panels, are the number of days in which they found enhanced ISOs and suppressed ISOs in the period they looked at, which I think goes from 1994 to 2017 or so, that you can look up. But the main story is that there are off-equatorial heat content maxima under the convective region, and there are these anomalies, and vice versa. Here you have positive heat content anomalies in the same place and negative heat content anomalies in the off the equator during the suppressed phase, which is very counterintuitive, right? Obviously that means that the processes that are determining the sea surface temperatures are very different than from the processes that are determining the heat content. So they went ahead and produced more analysis to show that when you look at sea surface height in terms of shading, which is a proxy for thermocline depth and hence heat content, and the currents associated with the anomalies associated with those phases as they defined here. So they take the Rossby wave, they create EOFs, empirical orthogonal functions, and they define phases. So we have 8 phases here. Each phase has a certain number of days that went into the composites that they made. But the main story is that when you have convection, you have westerly wind anomalies behind them, which kicks off a downwelling Kelvin wave, which goes and hits the coast and then begins to return as a upwelling Rossby wave. So the change of sign happens here, and there is some signature that goes off as coastal Kelvin waves into the Bay of Bengal and around and down into the Indonesian region to the south. So the poleward propagation of equatorial Kelvin waves into coastal Kelvin Kelvin waves is very well known. So basically looking at phase 1, 2, 3, 4 and so on, the idea is that the convective phase and the westerly anomalies are then replaced by easterly anomalies in a few days. The scale is related to how fast these waves move, and you can see the scale of the winds and currents here. We'll see other figures in a minute. So now these upwelling Rossby waves are propagating westward, as you would expect, with peaks off the equator, and then the wind forcing, easterly wind forcing, is reinforcing the Rossby waves, so it's strengthening the Rossby waves, and you can see that they are going off, hitting the west coast, and then they are going to return as upwelling Kelvin waves. So you are basically going to have a cycle of waves within the ocean which are determining the heat content response to convection activity in the deep tropics. So Kelvin waves reflecting as Rossby waves, and then forcing the Rossby waves, the free Rossby waves are forced by the anomalies that follow the convective phase during the dry phase, and you have this ocean feedback which they show here. So you can say here we are starting with the convective phase, so you can see this tall clouds with the stratus extending back as we see in the typical MJO structure. So you have the blue arrows which are the surface wind anomalies, and the thin black arrows which are the ocean currents. So those the Kelvin wave runs ahead of the convection, obviously moves much faster, hits the eastern boundary, piles up the mass because it's pushing the thermocline down and creating convergence of warmer waters, and the pressure gradient that's created is going to propagate westward as free Rossby waves, and then the easterlies are going to return once the convective phase is gone. As you can see, convective phase has gone. In this phase you are kind of indicating that there is maybe next convection beginning to try to organize. So now you have easterly winds and westward currents. We don't say easterly currents in the ocean. We typically talk about eastward and westward currents. In atmospheric, people prefer easterlies and westerlies. So again, currents and winds are in the same phase, but the reflected Rossby wave that had started here earlier and getting reinforced by these easterly winds is going to return to create a convergence in the middle. And that's the main point of this paper, that the convective activity and central Indian Ocean heat content are in phase because of these ocean wave processes. And then once this convection happens again, and you get back to the phase that we started with, where you have convection triggering westerlies to the west of the convection and creating downwelling Kelvin wave, which then again starts this loop. Okay, this is in a composite sense. Obviously each year is different, number of events are different in each year, and we are saying intraseasonal oscillation, but obviously we are mostly focused on the Rossby waves. The other interesting example is from a paper by Andy Weber, which he also has many papers, and his main argument is that the ocean Rossby waves are able to create conditions to trigger what are called primary MJOs. Secondary MJOs are where you have things like this. So lag 0 here is when there is convective activity on the equator. If you go before that, you have a positive OLR anomaly, which means you have a dry phase that has happened and has created the conditions for organizing this convection. So you can see the negative precipitation anomalies and positive precipitation anomalies and so on. So the secondary MJOs are basically where they are going across the maritime continent into the East Pacific, the Atlantic, and coming back to the Indian Ocean side and getting re-energized. So that's the idea created, being argued here, that in the Western Central Pacific, the secondary phases have a preceding dry phase Rossby wave, sorry, we are going eastward, so we have to be careful, Kelvin wave, whereas in the primary Rossby event, the argument is that there is no such propagation preceding the convective phase, and then there is evidence of the ocean Rossby wave activity that is creating conditions that are able to trigger primary MJOs. So the Rossby waves and Kelvin waves that we talked about before are now able to create these conditions in the Western Indian Ocean for the next phase or the next primary MJO after no preceding MJO has occurred. Okay, so you can imagine that these are kind of heuristic arguments, because in the observations and the model experiments are done based on some observations. This is just showing that kind of feedback here. So going back to about -100 days, looking at sea surface height, which is indication of thermocline and heat content, the ocean equatorial Rossby wave is shown propagating westward, going, I hope these are, yes, so going from -100 days and approaching here the latitudes, the longitudes where convection is being organized, and then you have the primary Madden-Julian oscillation getting kicked off related to the heat content buildup, SST, warm SST, and so on, that are organized to trigger the next MJO. So you can see here there is the maritime continent, there is Africa, and the downwelling Rossby wave going this way is basically going to lift the thermocline westward. So you can see the thermocline here, and it's going to deepen the it's a downwelling Rossby wave, so it's going to deepen the thermocline ahead and create these warm SSTs and trigger a primary MJO event. Okay. The other ocean feedback mechanism proposed here is similar, so it's arguing not so much for primary MJO but generally local convection preferred. So again, you start here. MJO convection has westerlies just behind it, triggers a downwelling Kelvin wave which deepens the thermocline towards the east. The downwelling Kelvin wave reflects into downwelling Rossby wave. So you can see the time scale here. That wave takes about 20 days. In about 35 days, you have the downwelling Rossby wave lifting the thermocline behind and suppressing it ahead of it, and is going to create deeper thermocline heat content and warm SST anomalies in the Western Indian Ocean and trigger local convection. Okay. You can read these papers, which are actually very nice, and I just included them briefly just to show you that at intraseasonal timescale, ocean is not just responding to MJO forcing or meso forcing, which is typically what many of the studies did before, looking at how the ocean is responding to the wind anomalies and heat flux anomalies and freshwater anomalies associated with MJOs and mesos, which we looked at before. But here we are looking at delayed feedbacks to the intraseasonal timescale variability from the ocean processes. Even though the ocean waves are forced by coupled or atmospheric processes, the interest here is to look at ocean feedbacks. So I hope that helps. You can please go ahead and read the papers to make sure that this short introduction just serves as a motivation rather than the complete detailed story. Okay.